Robots and vehicles see the world while moving through it. Through first-hand experience, we found that such on-the-go footage can be motion blurred, sometimes at critical moments, and that makes many vision tasks harder, including object detection. This led us to study, how much does motion blur, induced by ego motion, hurt object detection, and what can be done about it? Using MS COCO, we can measure detection accuracy on the vertical axis as a function of ever-increasing blur, plotted here from left to right. Unfortunately, detection performance drops off quickly with increased exposure. Ideally, the real-time baseline's 58.5% MAP at 50 on sharp images would hold steady, even when the images are blurred. On the surface, it seems there should be multiple remedies. Empirically, we found 3 remedy types that helped only somewhat, plotted here with similar colors, and nicknamed deblur, augmix or mini batch normalization, and squint. But 2 other types of remedies make the most difference, combined and plotted here as ours, specializing by exposure and training on expanded labels. We illustrate these different models next. To yield a usable online system, this investigation was carried out with a ResNet 50 feature pyramid backbone and faster RCNN baseline. Deblur means running a state-of-the-art image deblurring model as a preprocess at test time. The 2 out-of-distribution approaches are augmix and mini batch normalization. The former seeks robustness through training time augmentations, while the latter normalizes, accounting for test time statistics. Squint estimates the blur kernel to directionally undersample the image, before passing it through the backbone, and then undoes the sampling on outgoing activations. However, the 2 remedies that combine to make up our proposed algorithm are label modification, where training is performed using augmented images whose bounding box labels are specifically translated and expanded, with blur extent selection that sorts incoming images into specialized categories of exposure and type. Let's visualize the impact on real blurry images. The original model can detect objects, especially if they are fairly large, but it struggles to cope when the exposure is longer or the objects are smaller. Our model isn't perfect, but usually its detection accuracy is more tolerant of blur. In this sequence, the background people are especially better off with our approach. As are the people in this courtroom scene. Of course, periods with sufficiently fast motion blur test the limits of our approach as well. To objectively validate that we have improved detections, and not just on possibly cherry-picked examples, we follow existing works that synthetically blur images with known labels, for example, those from MS COCO. On the left, we show the initial sharp images with ground truth labels, then a randomly blurred version, showing the baseline model's detections in the middle, and our detections on the right. We also indicate if our model did better, worse, or approximately equal compared to the baseline. The extent of motion blur is random in each row, frequently choosing milder blur settings in line with blur from mobile phone photographs. Overall, our object detection model has improved handling of camera-induced motion blur. Thank you for watching.